More than 1 million miles from our world, a silent observer is steadily redrawing our map of the cosmos. For many generations, scientists had worked with the understanding that the universe, while almost incomprehensibly vast, was finite and measurable, extending roughly 14 billion light-years in all directions. But when the James Webb Space Telescope pointed its golden mirrors toward a patch of what appeared to be empty blackness, that long-held confidence began to fracture. The telescope's initial observations revealed galaxies taking shape far sooner than our existing models had predicted, and supermassive black holes expanding at a rate that current theories cannot yet explain. It also found cosmic structures already in place when the universe should have been in its earliest, most formative stages. The most profound revelation, however, is not merely how far into the past Webb can see. It is the question this new vision raises about the true scope of reality and the truly unsettling possibility that a vast portion of the universe may lie forever beyond our observational grasp. If you are ready, let us explore the new cosmos that the James Webb Telescope is now unveiling. To fully appreciate what the James Webb Space Telescope is showing us, we must first re-examine a simple yet profoundly misleading assumption about the universe: the idea that we can look across space as if it were a static landscape stretching out before us. In actual truth, the cosmos does not function in the same way as a terrestrial landscape. Out here, distance is not merely a measure of separation, it is also a measure of time. Light moves at a constant, unwavering velocity of approximately 300,000 kilometers per second, which is the ultimate speed limit in our universe. This is swift enough to race around the entire Earth more than 7 times in a single second. At the scale of our human experience, this speed feels instantaneous, so much so that our senses perceive light as arriving the very moment it is emitted. Across the immense voids of the cosmos, however, even light cannot conquer the delay imposed by distance. The moment a photon of light departs from its source, its long journey through time begins. When you glance across a room, for example, you are technically seeing into the past by a few billionths of a second, a delay so infinitesimal that our brains are built to simply disregard it. If you look toward a distant building, that delay extends into millionths of a second. Even then, the effect remains too small to register in our daily lives. Yet the universe operates on scales that dwarf our everyday experience, and it is precisely on these grand scales that the true nature of light and time becomes fully apparent. When you gaze up at our own moon, the light that reaches your eyes has been traveling for about 2 seconds. The serene lunar disk you see is not the moon as it is in this exact moment, but as it existed 2 seconds ago. When we turn our attention to the sun, this time delay expands to roughly 8 minutes. Sunlight must traverse 150 million kilometers of space to reach our planet. This leads to a remarkable thought experiment. If the sun were to suddenly cease to exist, our sky would not immediately plunge into darkness. For a full 8 minutes, sunlight would continue to stream toward us, carrying the final message from a star that was already gone. From our solar system outward, these time delays grow to staggering proportions. The closest star beyond our own sun, Proxima Centauri, appears to us not as it is today, but as it was more than 4 years in the past. When astronomers point their telescopes toward the center of our Milky Way galaxy, the light entering their instruments began its long voyage approximately 26,000 years ago, long before the rise of the earliest known human civilizations. And when we observe the Andromeda Galaxy, our nearest major galactic neighbor, the light we capture today actually departed from its stars about 2 million years ago, a time well before recorded history, when modern humans had not yet spread across the globe. The night sky, therefore, is not a live snapshot of the universe. It is, in effect, a profound historical document, a layered archive of cosmic events. Every star, every galaxy, and every faint glimmer of light carries with it an implicit timestamp, marking the moment its light embarked on a journey across the cosmos. Each photon arriving at Earth today has been traveling for years, centuries, or even billions of years. The farther away an object is, the more ancient the story its light has to tell. Yet, the universe does not preserve these ancient messages without altering them. One of the most fundamental properties of our reality is that space itself is expanding. This concept may sound abstract, but its consequences for how we observe the cosmos are immense. Galaxies are not simply drifting away from each other through a static, empty void. Instead, the very fabric of space-time is stretching, systematically increasing the distance between all galaxies over cosmic ages. And as space stretches, the light traveling through it is stretched as well. As a photon of light crosses billions of light-years of expanding space, its wavelength is gradually elongated. Energetic, short wavelength blue light is pulled toward the longer wavelengths of red light, and eventually, it shifts completely into the infrared spectrum, which is invisible to the human eye. Astronomers refer to this phenomenon as redshift. More than just a change in color, redshift functions as a kind of cosmic timestamp. The more a photon's light has been stretched, the longer its journey has been, and thus the earlier in the universe's history it must have been emitted. In this way, distance and time become inextricably linked. To look farther out into space is to look deeper into the past. For decades, astronomers depended on telescopes primarily designed to observe visible light, the narrow band of the electromagnetic spectrum that our eyes evolved to see. Powerful instruments like the Hubble Space Telescope completely transformed astronomy, delivering breathtakingly detailed images of galaxies, stellar nurseries, and nebulae throughout the nearby universe. Yet, as scientists attempted to push their observations further back in time, toward the very dawn of cosmic history, the universe started to seem strangely barren. This was not because the early universe was truly empty, but because its most ancient light had fundamentally changed its form. As light from the earliest galaxies journeyed across the expanding cosmos, its wavelength was stretched far beyond the visible spectrum. By the time this ancient light finally arrived at Earth after billions of years, much of it had shifted into infrared wavelengths that earlier telescopes were not designed to perceive. To these instruments, vast regions of the early universe appeared dark, but this apparent darkness was an illusion. It was not a sign of emptiness, but rather a sign of light that had moved beyond our technological capacity to see it. The universe was still there, waiting to be discovered. The James Webb Space Telescope was engineered specifically to perceive this hidden ancient light. Instead of concentrating on visible wavelengths, Webb is a master of the infrared, built to capture faint signals from galaxies whose light has been traveling for over 13 billion years. Its magnificent primary mirror spans more than 6 meters across and is coated with an exquisitely thin layer of pure gold, a material specifically chosen for its exceptional ability to reflect infrared light. This design allows Webb to gather the incredibly faint, redshifted signals that were entirely missed by its predecessors. However, detecting infrared light presents an immense technical hurdle. Infrared radiation is fundamentally linked to heat. Any object with warmth emits it, including the telescope itself. If Webb were to become even slightly warm, it would glow brightly in the very same infrared wavelengths it is trying to observe, effectively blinding itself and drowning out the delicate signals arriving from the distant universe. Tucked behind its massive sunshield, in perpetual shadow, the James Webb Space Telescope chills to a frigid negative 230 degrees Celsius. Only at such extreme cold can its instruments become sensitive enough to register the quietest murmurs of light from the dawn of time. Its operational orbit is situated nearly 1.5 million kilometers from our planet, at a gravitationally stable location called Lagrange Point 2. From this remote outpost, protected from the blinding glare and thermal noise of the Earth and Sun, Webb is free to gaze into the cosmos for extended periods, completely undisturbed. When the telescope directs its golden mirrors to a patch of sky that our own eyes would see as utter blackness, it is not looking at nothing. It is engaged in a patient vigil, waiting for individual photons that started their cosmic journey when the universe itself was in its infancy. These messengers from the past do not arrive in a flood, but often one by one, each carrying a faint trace of a galaxy whose light has journeyed for billions of years across expanding space. To capture these whispers, Webb might fix its gaze on a single sliver of the heavens for hours, or even days. It patiently gathers these ancient particles of light, allowing a detailed image to gradually materialize from the void. And when the picture is complete, what emerges from the darkness is not the expected emptiness. Instead, galaxies bloom into view where none were thought to exist. We see systems already churning out new stars, already assembling complex structures, and evolving in ways that defy our previous models. The infant universe, it turns out, was not a quiet, fragile nursery. It was a place of vibrant and powerful activity. Every image the telescope produces is therefore far more than a simple photograph. It is a deep historical mosaic, assembled from light that has traversed billions of years to reach us. By the time this ancient light finally arrives, the stars that created it may have long since vanished, and their host galaxies may be utterly transformed. What we are witnessing, then, is not the universe as it exists now, but a ghostly echo of its past. For this reason, astronomers view telescopes like Webb as time machines. Nearby galaxies show us the cosmos in its more recent state, while increasingly distant ones reveal progressively earlier chapters of cosmic history. Yet, even the phenomenal power of the James Webb Space Telescope has a fundamental boundary. There exists a horizon beyond which no instrument, no matter how advanced, can possibly see. This is not due to a failure of technology, but a consequence of the universe's own physics. Since the cosmos began, light has only had a finite time to travel. This imposes a maximum distance from which any signal could have reached us. Astronomers refer to this boundary as the observable universe, not an edge to space itself, but an edge to our information. Beyond this cosmic horizon, the universe certainly continues. Galaxies are born, stars ignite and collapse, and black holes merge in vast regions of space-time whose light is destined never to reach Earth, carried away by the relentless expansion of space. The James Webb Space Telescope has not shown us the edge of existence. On the contrary, it has helped us appreciate how much of reality must lie forever beyond our observational grasp. As the telescope peers ever closer to this ultimate boundary, detecting galaxies from earlier and earlier epochs, a profound realization takes hold. If the cosmos was already so rich and complex at the very limits of our sight, it suggests that the true entirety of all that exists, both seen and unseen, must be of a scale that dwarfs even our most daring imaginations. For decades, astronomers held a well-established model for the dawn of the cosmos. The story began with the Big Bang, which filled space with a hot, uniform soup of matter that subsequently expanded and cooled. In this scenario, gravity acted as a patient sculptor, slowly gathering material over immense timescales. Minor fluctuations in the density of this primordial matter gradually amplified, pulling in gas to form the very first stars and galaxies. This narrative of cosmic evolution was elegant and logical, but it implied that the process would be slow. The earliest galaxies were expected to be small, dim, and structurally simple fragile collections of stars just beginning to coalesce. Consequently, when Webb first turned its gaze toward these distant eras, scientists anticipated finding a sparse landscape, dotted with only a few of these primitive galactic seeds. What it found instead were bustling cosmic cities. The telescope revealed crowds of bright, substantial galaxies, appearing again and again in epochs where they were thought to be rare. These were not the faint, struggling proto-galaxies of theory. Many were already ablaze with light, forming stars at astonishing rates. The shock for astronomers was not in discovering one or two anomalies, but in recognizing a consistent pattern. The data presented a stark and repeating contradiction to the established narrative. Time after time, Webb detected galaxies in the universe's first few 100 million years that were far more massive and luminous than our models had ever predicted. Some of these systems already contain the mass of hundreds of millions, or even billions, of our own sun in stars. According to the long-standing timeline of galaxy formation, assembling such colossal structures should have required significantly more time. Gravity, while relentless, is not instantaneous. For galaxies to form, vast clouds of gas must first cool down and lose energy before they can contract, and halos of dark matter must grow massive enough to gravitationally trap this ordinary matter. Each of these fundamental steps requires millions of years, and yet, Webb's observations suggest these processes were happening far faster than we thought possible. Perhaps the most intriguing clue came from the chemical makeup of these unexpectedly mature galaxies. Within them, Webb's instruments detected the clear signatures of elements like carbon and oxygen. These heavier elements were not forged in the Big Bang itself. They are created exclusively in the nuclear furnaces of stars. They are only released back into the cosmos when those stars reach the end of their lives, often in violent supernova explosions. Finding these elements in such ancient galaxies implies that at least one full generation of stars had already been born, lived out its entire lifespan, and seeded the surrounding space with its remains before the galaxies we now see even took shape. The cosmic timeline appeared to be compressing, forcing us to rethink the very first chapter of cosmic history. It now seems that cosmic events, once thought to require hundreds of millions of years to play out, may have unfolded with astonishing speed. To understand the depth of this puzzle for astronomers, one might consider the process of building a modern city. You cannot erect skyscrapers before the roads are laid, nor can you pour concrete without first having produced the necessary steel. Each step is built upon the completion of the one before it. In this same way, the early universe was expected to be a time of laying cosmic foundations. Instead, what the Webb telescope appeared to reveal were cosmic structures already towering, as if the buildings were rising before the groundwork was even finished. This stark inconsistency between theoretical models and direct observation has become known among scientists as the problem of too much light, too early. When astronomers calculated the expected light output from galaxies in the universe's first billion years, their models consistently fell short of what Webb was actually seeing. The discrepancy was significant. In some instances, the observed galaxies shone several times more brightly than any prediction allowed. Whenever such a profound disagreement between theory and data arises, the first step for scientists is to exhaust simpler explanations. Could the measurements themselves possibly be flawed in some way? Perhaps dust within these distant galaxies was distorting the observations. Or maybe the immense gravity of intervening galaxies was acting as a lens, magnifying the light from these background systems and making them appear brighter than they truly are. Another potential explanation centered on the powerful presence of rapidly feeding supermassive black holes at the very hearts of these galaxies. As immense quantities of matter spiral into a black hole, the process can unleash a torrent of energy, creating intense light that could make a galaxy seem far more luminous or massive than its stellar population alone would suggest. These possibilities were, of course, investigated with great care. In certain cases, the additional brightness from actively feeding black holes did indeed account for some of the discrepancy. Factoring in their influence helped to revise some of the most extreme mass estimates for these early galaxies downwards. Yet, the fundamental pattern persisted across the data. Even after applying these corrections, the early cosmos still appeared to be populated with far more bright galaxies than our standard models could explain. The tension had been eased, but it was far from resolved. The Webb telescope continued to repeat these observations in different patches of the sky, employing multiple instruments and wavelengths, and the results were unwavering. The early universe was a place of surprisingly vigorous activity, with star formation proceeding at a pace that was simply not expected. This persistent anomaly forced astronomers to go back and re-examine one of their most fundamental assumptions: the efficiency with which the universe can transform raw gas into stars. In our modern cosmos, the process of star formation is known to be remarkably inefficient. The vast majority of gas inside a galaxy never condenses into a star. Instead, it is heated by radiation, churned by turbulence, or expelled entirely by powerful stellar winds and supernova explosions. Only a tiny fraction of this material ever manages to collapse and ignite as a new star. It raises the question of whether the early universe might have operated under a completely different set of rules. One possibility is that the conditions were simply much denser. In the youth of the cosmos, galaxies were closer together, and the clouds of gas from which they formed were more tightly packed than they are today. Under these conditions, frequent collisions between galaxies could have compressed vast quantities of gas, triggering intense and rapid bursts of star formation. Another line of inquiry involves the very composition of the earliest gas clouds. The first stars were forged from almost pure hydrogen and helium, lacking the heavier elements that are known to influence how gas cools and collapses in the modern universe. These simpler primordial conditions may have enabled pathways for star formation that are no longer common in galaxies today. Galactic mergers likely played a crucial role as well. When two galaxies collide, their gravitational interaction can drive enormous amounts of gas toward their centers, where it becomes compressed and heated. This process is known to ignite powerful waves of star formation, capable of producing a huge number of stars in a comparatively brief period. While each of these explanations may contribute a piece to the solution, none of them, either alone or in combination, has been able to fully resolve the mystery. Deepening the enigma, Webb has also found evidence of supermassive black holes existing much earlier in cosmic history than previously thought possible. Some of these colossal objects appear to have already formed when the universe was less than 500 million years old. Despite their young age, they contain masses equivalent to millions or even billions of our Sun. According to conventional theories, black holes begin as the collapsed remnants of massive stars and typically contain only a few tens of solar masses. Growing these seeds into supermassive objects should require long, steady periods of feeding and numerous mergers over cosmic timescales. Yet, Webb continues to find these giants at astonishingly early epochs. This has compelled astronomers to seriously entertain possibilities that once seemed on the fringe of theory. Perhaps the very first stars were far more massive than any that exist today, allowing them to collapse directly into large, heavy seed black holes. Another idea is that enormous clouds of primordial gas could have collapsed directly into a black hole, bypassing the star formation stage altogether. Or, perhaps most intriguingly, the early universe may have harbored unique conditions that permitted black holes to grow far more rapidly than our current understanding allows. For now, none of these hypotheses has been confirmed, but the data is so compelling that none can be dismissed. What makes these discoveries so profoundly important is that the earliest galaxies were the architects of everything that followed. Their intense radiation fundamentally altered the state of gas throughout the cosmos. The supernova explosions of their first stars seeded space with the heavy elements necessary for life, and their collective gravity sculpted the large-scale structures that would eventually evolve into the galaxy clusters and cosmic filaments we see today. If galaxies formed earlier and grew faster than we believed, then the entire timeline of cosmic evolution may need to be revised. The universe, it seems, may have assembled its first major structures far more quickly than scientists had imagined. As the James Webb Space Telescope continues its journey, peering deeper into space and further back in time, a consistent picture keeps emerging. The early universe was not a quiet, hesitant place. It was already a whirlwind of creation. Stars were igniting, galaxies were growing, and black holes were voraciously gathering mass, all within a cosmic era once thought to be nearly empty and still. It seems the universe did not wait. It began building itself almost from the very beginning. For much of modern astronomy, it was believed that a solid answer had been found for one of the grandest questions imaginable. How many galaxies populate the universe? The method developed seemed both straightforward and elegant, despite the extraordinary scale of the task. Astronomers would aim a powerful telescope at a tiny, seemingly empty patch of the night sky. Within that small region, they would meticulously count every visible galaxy and then use that number to estimate how many similar regions could fit across the entire celestial sphere. The logic was simple. If you can determine the number of galaxies in a representative sample of the universe, you can scale that figure up to approximate the total for the whole. When the Hubble Space Telescope conducted one of its most profound observations, the outcome left even its own scientists in awe. Gazing at a region of the sky so minuscule it could be obscured by a grain of sand held at arm's length, Hubble unveiled a staggering tapestry of nearly 10,000 galaxies. This image, which would become celebrated as the Hubble Ultra Deep Field, fundamentally altered our perspective on the cosmos. Before this moment, a common astronomical assumption was that the universe would appear increasingly barren the farther our telescopes could see. Hubble proved the exact opposite to be true. The deeper it peered into the darkness, the more galaxies materialized from the void. Based on these groundbreaking observations, astronomers revised their census of the cosmos, estimating that the observable universe likely held between 100 and 200 billion galaxies, a number so vast that it borders on the incomprehensible. For years, this remained our best approximation of the universe's population. Then, the James Webb Space Telescope turned its powerful gaze toward that same profound darkness, and our understanding shifted once more. Where previous images had depicted scattered islands of light adrift in an ocean of black, Webb began to reveal deeper, more intricate layers of structure. Areas that had once registered as empty began to emit a faint, ethereal glow in infrared light. Slowly, galaxies that had been completely imperceptible to earlier instruments emerged from the cosmic background. This was not an indication of any error in the prior observations. Instead, it was a matter of looking for the right kind of light. As light journeys across billions of years of an expanding cosmos, its wavelengths are stretched. Light that was originally emitted in the visible spectrum is gradually elongated, shifting into the infrared. By the time this ancient light finally reaches our telescopes on Earth, much of it has moved far beyond the detection range of older instruments. The galaxies were not absent. Their light had simply drifted beyond the limits of our vision. The James Webb Space Telescope was engineered specifically to capture this stretched ancient light. Its instruments possess an extraordinary sensitivity to infrared radiation, granting it the power to unveil galaxies that were previously hidden from us. When Webb commenced its own deep field observations, it once again targeted regions of the sky that seemed almost entirely empty. But where Hubble saw thousands of distant objects, Webb uncovered dense, overlapping layers of galaxies, stacked one behind the other across the expanse of cosmic time. In some of these deep surveys, hundreds of thousands of individual galaxies have been identified within a relatively small celestial patch. The sheer scale of this discovery is difficult to overstate. Each of these individual points of light is a galaxy containing an immense number of stars, some holding billions, others even trillions. Many are also home to vast clouds of gas and dust, where new stars are actively being born, and it is highly probable that countless planetary systems orbit within them. The universe, as it turns out, is not a sparsely populated expanse of isolated galaxies. It is, in fact, astonishingly crowded. What makes this revelation even more remarkable is that Webb is capable of more than simply detecting these galaxies. It can measure them in detail. By analyzing the redshift of their light, astronomers can calculate how far away each galaxy is, and by extension, how far back in time we are seeing it. This allows us to witness the universe as it was in its youth. Furthermore, Webb can estimate the rate at which these early galaxies were forming stars and even approximate their total mass. When scientists bring all of these measurements together, they can begin to assemble a history of galaxy formation across billions of years of cosmic evolution. And as this cosmic history takes shape, a truly striking pattern begins to come into focus. Galaxies are not distributed randomly throughout space. Instead, they congregate and organize themselves into immense, interconnected structures that stretch across hundreds of millions of light years. These formations take the shape of enormous filaments, linking vast clusters of galaxies together in long, delicate strands that span truly unimaginable distances. Situated between these filaments are enormous voids, vast regions of space containing very few galaxies. When viewed as a whole, this grand arrangement resembles a gigantic, three-dimensional web. It is this magnificent structure that astronomers have named the cosmic web. This intricate pattern is not a product of chance. It emerged organically from the earliest moments of the universe's history. In the immediate aftermath of the Big Bang, matter was distributed with near-perfect uniformity all throughout space. However, infinitesimally small fluctuations in density were present from the very beginning. Regions that were slightly denser than their surroundings exerted a slightly stronger gravitational pull. Over the vast course of cosmic time, matter was slowly drawn toward these denser areas, amplifying the initial differences. Gravity steadily pulled material inward, forming the dense filaments and clusters we observe today, while leaving behind the immense voids where very little matter remained. A helpful way to visualize this cosmic process is to imagine rainfall moving across a landscape. Water naturally flows downhill, gathering in valleys and carving out a network of rivers. Over time, this process creates a structured system of channels, while the higher ground remains comparatively dry. In a strikingly similar fashion, matter flowed throughout the early universe under the steady influence of gravity, gradually sculpting the vast filaments and clusters that now define the cosmic web. This gravitational sculpting is what gave the universe its fundamental architecture. The James Webb Space Telescope is now helping astronomers map this structure with a clarity that was never before possible. By detecting extremely distant and faint galaxies that were previously invisible, Webb is effectively filling in the missing pieces of our cosmic map. Entire populations of faint galaxies have now materialized in areas where earlier surveys recorded only darkness. This work is profoundly important because the distribution of these galaxies is more than just a visual spectacle. It holds the very secrets to how the universe evolved. The way galaxies cluster together reveals how matter has moved through space over billions of years, how gravity has shaped large-scale structures, and how the tiny fluctuations in the early universe ultimately grew into the vast cosmic architecture we observe today. Webb's observations have already yielded surprising insights, showing that many of these large-scale structures began to form remarkably early in cosmic history. Some long, well-defined filaments of galaxies were already firmly in place when the universe was only a few billion years old. In certain regions, galaxies appear to be tightly grouped together, suggesting that gravity was sculpting massive clusters far earlier than many theoretical models had predicted. This discovery challenges our timelines for cosmic construction. Yet, the cosmic web is not defined solely by the matter it contains. It is equally defined by what it lacks. Between its dense, galaxy-rich filaments lie the enormous cosmic voids, regions characterized by an almost complete absence of galaxies. Some of these voids are truly immense, spanning tens or even hundreds of millions of light years across. If an observer could somehow be placed near the center of one of these great voids, they might look out in every direction and see a sky of almost perfect, unending blackness. By volume, these voids are among the largest structures in the entire universe. The universe, in other words, presents a fascinating paradox. It is at once both incredibly crowded and profoundly empty. Dense clusters of galaxies are woven into immense filaments of matter, while vast regions of near-total darkness stretch between them. This is the fascinating dual nature of our cosmos, a grand and beautiful tapestry woven from both brilliant light and deep shadow. When astronomers analyze the deep field images captured by the Webb telescope to project the total number of galaxies in the observable universe, the results are simply staggering. The long-held estimate of 100 billion galaxies now seems to have been just a fraction of the complete story. If Webb's findings are indeed representative of the cosmos at large, the true count could be far greater, potentially reaching into the trillions. Each of these is an island of cosmic history, a container of stars and planets unfolding its own narrative across eons. Yet, this almost incomprehensible number still only describes the portion of the universe within our view. Beyond this observational limit, space continues, galaxies persist, and the cosmic web stretches into domains whose light is fated to never reach us. If the cosmos is this rich within the boundaries we can perceive, what does that suggest about the true, unimaginable scale of everything that lies beyond? At first consideration, determining the size of the universe might seem like a straightforward calculation. The Big Bang is understood to have occurred approximately 13.8 billion years ago. Since light travels at a fixed speed, it feels intuitive to conclude that the most remote objects we can detect should be about 13.8 billion light-years away. In the context of our daily lives, this line of reasoning appears perfectly sound. The reality of the cosmos, however, is far more astonishing. In truth, the observable universe possesses a radius of roughly 46 billion light-years, which gives it a total diameter of about 93 billion light-years. This figure is neither speculation nor an exaggeration. It is a direct consequence of precise measurements of cosmic expansion and our understanding of how ancient light behaves as it journeys through space. The reason this result can feel so counterintuitive is that it clashes with our innate assumptions about motion and distance, challenging us to think beyond our terrestrial experience. This apparent paradox does not mean that anything is moving through space faster than the speed of light. That fundamental rule of physics remains unbroken across the entire cosmos. No galaxy is hurtling through the void at impossible velocities, and no signal is violating the ultimate limit established by nature. The confusion stems from a common misunderstanding of cosmic expansion, which is not about objects flying outward from a central point. Instead, the universe is expanding in a much stranger and more profound way. When astronomers describe distant galaxies as moving away from us, the language can easily conjure an image of ships sailing out from a port into an empty ocean. On the largest scales, however, galaxies are not truly traveling times through time-space in this manner. What is actually happening is that the space between galaxies is gradually stretching, which in turn increases the distance that separates them. This process is often illustrated with a helpful analogy. Imagine drawing small dots on the surface of a balloon. As the balloon is inflated, every dot moves farther from every other dot. This is not because the dots are sliding across the rubber, but because the surface itself is expanding. From the perspective of any single dot, all others appear to be drifting away, even though no dot occupies a special, central position. The large-scale expansion of our universe operates in much the same way. When a faraway galaxy released the light that our telescopes capture today, it was significantly closer to our own cosmic neighborhood than it is now. Over the billions of years that this light traveled toward Earth, the universe itself continued to expand, steadily stretching the distance between all galaxies. By the time that ancient light finally completed its journey and arrived here, the galaxy that emitted it had already been carried tens of billions of light years farther away by the expansion of space. This is precisely why we can observe galaxies whose light has journeyed for over 13 billion years, even though those same galaxies now reside at a much greater distance. The light did not cross a fixed expanse. It traveled through a space that was continuously growing throughout its journey. In effect, the path the light had to traverse was lengthening as the light moved along it. In the early history of the universe, the rate of expansion was slower, which permitted light to make consistent progress across space. Over the course of billions of years, however, the expansion of the cosmos began to accelerate, stretching distances at an ever-increasing pace. Some photons started their journeys early enough that they could eventually reach us despite this acceleration, while others, emitted from more distant regions, never will. This dynamic naturally establishes a boundary, but it is not a physical wall or an edge in the conventional sense. Astronomers call this limit the cosmic horizon. It marks the farthest distance from which light has had enough time to reach us since the beginning of the universe. Beyond this horizon, space and galaxies certainly continue to exist, but the light from those regions has simply not had a sufficient amount of time to arrive at our location. The crucial takeaway is that the cosmic horizon does not signify the edge of the universe itself. It only represents the boundary of what is observable from our specific vantage point in space and time. Several independent lines of evidence strongly indicate that the universe extends far beyond this boundary. When astronomers map the distribution of galaxies across the sky, they find no evidence of their density diminishing towards some ultimate edge. Instead, the cosmos appears broadly uniform in every direction we look. Furthermore, the faint afterglow of the Big Bang, known as the cosmic microwave background, is also remarkably consistent across the entire sky. This pattern would be extraordinarily improbable if space simply ended just beyond our visible sphere. All of this evidence points toward a simple, yet deeply unsettling conclusion. The universe almost certainly stretches far beyond the portion we can see. Beyond our cosmic horizon, there may be countless more galaxies, clusters, and vast cosmic structures, but their light will never reach us, as the space between us and them is expanding too rapidly for light to overcome. Even more fascinating is the fact that the cosmic horizon itself is not a fixed boundary. As time moves forward, our observable universe gradually becomes larger, because light from ever more distant regions has had more time to travel toward us. In this sense, our horizon slowly expands outward, revealing new parts of the cosmos. At the same time, however, the accelerating expansion of space means that the distances between galaxies are growing faster than they did in the past. These two processes work together in complex ways. While some galaxies that were once invisible may eventually cross into our view as their ancient light finally arrives, others are being carried away from us so quickly that they are receding beyond our reach, their light forever lost to the ever-expanding void. As cosmic expansion continues, a silent migration carries distant galaxies so far from us that their light radiated today will never reach our planet. Over immense timescales, these galaxies will gradually fade from our perception, vanishing from sight. If the universe's expansion proceeds at its current pace, observers tens of billions of years in the future may see a profoundly different vista. With nearly every galaxy outside our local group having drifted beyond the cosmic horizon, their sky would contain only a small collection of neighboring galaxies in an otherwise empty expanse. From their isolated vantage point, it might seem the entire universe consisted of just this handful of star systems. A chilling thought arises. They might never know the cosmos was once alight with trillions of galaxies. This concept fundamentally alters our understanding of observation. The observable universe is not a fixed, universal boundary, but is instead entirely dependent on an observer's location in space-time. An observer in a galaxy billions of light-years away perceives a different sphere of the cosmos than we do, one including regions of space forever inaccessible to us. In effect, every point in the universe is the center of its own unique observable bubble. This means there is no single, privileged viewpoint from which all of existence can be witnessed. This is precisely why instruments like the James Webb Space Telescope are so revolutionary. By detecting galaxies nearer our cosmic horizon than ever before, Webb extends our observational window to the edge of what physics permits, unveiling structures from the universe's infancy. Even with its incredible power, the Webb telescope cannot peer beyond this horizon. The galaxies it captures at the fringe of the observable universe are not as they appear in its stunning images. Their light embarked on its journey billions of years ago, and during that vast time, the universe has continued to expand. The galaxies themselves have likely transformed dramatically since emitting the light we now receive. What we are observing, then, is not the universe as it is, but a mosaic of ancient signals from countless different moments in cosmic history. Beyond the boundary from which these signals originate lies a much larger cosmos, one that will remain permanently concealed from view. The James Webb Space Telescope has not located an edge of the universe. It has revealed a more profound truth that the cosmos may stretch on, far beyond what any observer, anywhere, can ever hope to see. For much of the 20th century, the story of the universe appeared to be on a clear trajectory. The Big Bang initiated a grand expansion, while gravity slowly began sculpting the cosmos. Galaxies coalesced into clusters, stars ignited within swirling gas nebulae, and the universe's large-scale structure gradually took shape. This picture was built upon a simple, intuitive assumption. Gravity, the force drawing matter together, was expected to act as a cosmic brake, slowing the expansion over time. Since every galaxy has immense mass, and mass attracts other mass, astronomers presumed the outward momentum from the Big Bang must be steadily diminishing. The galaxies flying apart were thought to be slowing, as gravity's relentless pull tugged them back toward one another. For decades, the central debate in cosmology was not whether the expansion was slowing, but the rate at which it was happening. Some scientists theorized that gravity might one day be powerful enough to halt the expansion and then reverse it. This would lead to a future where the universe collapses back upon itself, an event poetically described as the Big Crunch. Then, toward the close of the 1990s, two independent teams of astronomers made a discovery that would permanently alter this narrative. They were studying distant stellar explosions known as Type Ia supernovae, which occur when certain stars reach a critical mass and detonate with incredible brilliance. Because these explosions achieve a nearly uniform peak luminosity, they serve as exceptionally reliable cosmic mile markers. By comparing a supernova's apparent brightness to its known intrinsic brightness, scientists can accurately calculate its distance. When this distance is cross-referenced with the host galaxy's recession speed from Earth, astronomers can piece together the history of cosmic expansion. The results were nothing short of astonishing. The universe's expansion was not slowing down at all. In fact, it was accelerating. Distant galaxies were found to be farther away than they should have been if gravity were the only force at play. The deeper astronomers peered into space, the more undeniable the pattern became. Instead of losing momentum, the expansion of the universe had been speeding up for billions of years. It was a finding suggesting some unknown force was actively pushing space apart. To account for this mysterious effect, cosmologists proposed a new concept, giving it the name dark energy. This was not a discovery of a new particle or substance, but rather the acknowledgement of a profound gap in our understanding. Dark energy cannot be seen or measured directly. It does not emit, absorb, or reflect any light or radiation our telescopes can detect. Its existence is purely inferred from its large-scale influence on cosmic expansion. Yet, despite its invisibility, dark energy appears to be the dominant component of the universe. Current measurements indicate that approximately 68% of the cosmos is composed of dark energy. By contrast, ordinary matter, the atoms forming stars, planets, and ourselves, constitutes less than 5% of the total cosmic inventory. The remainder is believed to be dark matter, another invisible substance whose nature remains one of the greatest unsolved puzzles in physics. In essence, the familiar, visible universe is just a tiny fraction of what truly exists. What makes dark energy particularly perplexing is its behavior as the universe expands. As space grows larger, normal matter and radiation become diluted. A fixed amount of material spreads out over a greater volume, causing its overall density to decrease. Dark energy, however, does not follow this rule. Its density appears to remain almost perfectly constant, even as space itself stretches. This means, as the universe gets bigger, more dark energy seems to emerge to fill the new volume, increasing its total amount. This leads to a powerful feedback loop. The more the universe expands, the more dark energy there is, which in turn causes the expansion to accelerate even faster. Over billions of years, this process has fundamentally altered the balance of power in the cosmos. In the early universe, matter and its gravitational pull held sway. Today, the universe is firmly in the grip of dark energy. Gravity was the original architect of the cosmos, its immense pull gathering gas to construct the cosmic web of galaxies and clusters that our telescopes reveal today. But as the universe expanded, diluting matter across ever greater volumes of space, another force began to assert its influence. Roughly 5 billion years ago, this mysterious component, known as dark energy, became the primary driver of cosmic evolution. From that moment on, the expansion of space itself started to accelerate. While the James Webb Space Telescope cannot see dark energy directly, its presence is woven into the very fabric of the data it collects. The sheer scale of the observable universe, the profound stretching of ancient light, and the rate at which distant galaxies retreat from us all bear the signature of this accelerated expansion. It raises a profound question: what would our universe look like without it? In a cosmos devoid of dark energy, the cosmic horizon would be much nearer, as the expansion would have decelerated more significantly over the eons. Many of the faraway galaxies that Webb now captures in stunning detail would never have reached the positions we currently observe. In a very real sense, dark energy has stretched the fabric of the universe, allowing the observable cosmos to attain the breathtaking scale we witness. Yet, its influence extends beyond shaping the present. It also dictates the universe's ultimate fate. If dark energy's behavior remains consistent with our current observations, the cosmic expansion will continue to speed up indefinitely, while gravity will maintain its hold on local structures like galaxies and clusters. The distances between these cosmic islands will grow ever larger. Over unimaginable timescales, more and more galaxies will drift beyond our cosmic horizon, their light no longer able to reach us. Trillions of years into the future, an observer inside a galaxy like the Milky Way might gaze into a sky that appears almost entirely empty, save for its own stars and a few local companions. This makes our own era a rather special one. We exist in a time when the universe is old enough for countless galaxies to have formed, yet young enough that we can still see them. Even so, the narrative of cosmic expansion holds a deep and persistent puzzle that scientists are still working to solve. When astronomers attempt to measure the universe's current rate of expansion, two distinct methods yield two slightly different results. One technique delves into the distant past, studying the cosmic microwave background, the faint afterglow of creation, from when the universe was only 380,000 years old. Patterns embedded within this ancient light enable scientists to calculate an expansion rate of approximately 67 kilometers per second for every megaparsec of distance. A second method, however, concentrates on the local universe. Here, astronomers gauge distances to nearby galaxies using reliable markers like Cepheid variable stars and type Ia supernovae, then compare those distances to the speeds at which the galaxies are receding. This approach consistently returns a higher value, around 73 kilometers per second per megaparsec. Both of these methodologies depend on exceptionally precise observations and have been rigorously cross-checked with independent sets of data. Yet, even after years of intense scrutiny, the two figures stubbornly refuse to align. This conflict, known as the Hubble tension, stands as one of the most compelling mysteries in modern cosmology. The implications are significant. If both measurements are indeed correct, it suggests our current model of how the universe evolves may be incomplete. The James Webb Space Telescope was anticipated to bring clarity to this issue by refining the accuracy of distance measurements in the nearby cosmos. Instead, Webb's observations have only bolstered the evidence for the higher expansion rate. Rather than resolving the discrepancy, the new data has made the tension impossible to overlook. This leaves cosmologists contemplating several possibilities. There could be subtle, undiscovered errors concealed within one of the measurement techniques, or we may be seeing the first hints of new physics that influences cosmic expansion in ways we do not yet comprehend. Whatever the final explanation may be, the discovery of dark energy has already fundamentally reshaped our understanding of the universe. It showed us that the cosmos is not merely expanding, but accelerating. Dark energy actively stretches space, pushing distant galaxies ever farther apart and defining the cosmic horizon that marks the edge of what we can observe. Yet, it represents only one half of the invisible forces governing the cosmos. While dark energy drives things apart on the largest scales, another force must be responsible for pulling matter together on smaller scales, allowing galaxies, clusters, and the great structures seen by Webb to form in the first place. If dark energy determines the rate at which the universe flies apart, another unseen component dictates how it holds together. Without this second ingredient, the cosmos revealed by modern telescopes would be unrecognizable. Galaxies would have struggled to coalesce, clusters would have failed to form, and the vast, web-like patterns that span the universe would never have taken shape. This essential, hidden component is known as dark matter. It is a substance that does not emit, reflect, or absorb any light or radiation that our instruments can detect, making it, for all intents and purposes, completely invisible. The paradox, however, is that its gravitational influence is undeniable, and the quantity of it appears to be truly immense. Current estimates suggest that dark matter accounts for an astonishing 85% of all matter in the universe. This means that everything we consider familiar, from stars and planets to clouds of gas and dust, and even the atoms that make up our own bodies, constitutes just a tiny fraction of the cosmos's total mass. What our telescopes see is merely the illuminated surface of a far grander, unseen structure. The earliest clues that something invisible was shaping galaxies emerged nearly a century ago. Astronomers who were studying the rotation of spiral galaxies observed that stars in the outer regions were orbiting far more rapidly than expected. According to our understanding of gravity, these stars should have been flung out into the void of intergalactic space if only the visible matter was holding the galaxy together. But they were not escaping. Instead, the outer stars continued to circle at high speeds, as if they were embedded within enormous, invisible halos of mass. The visible stars and gas were just a small part of a much larger gravitational system, held together by the pull of something we could not see. As our view of the cosmos sharpened through the passing decades, compelling evidence for something unseen began to accumulate on the largest scales imaginable. Entire clusters of galaxies were found to possess a gravitational influence far greater than their visible matter could ever account for. When astronomers analyzed the movements of individual galaxies within these colossal structures, their motions strongly suggested the presence of immense quantities of hidden mass. The question became unavoidable. What could be holding these cosmic cities together so tightly? A second powerful line of evidence emerged from a phenomenon predicted by Albert Einstein's theory of general relativity: gravitational lensing. Because massive objects warp the very fabric of space-time, they can bend the path of light that passes nearby. Astronomers observed that when they looked at distant galaxies through the lens of a closer galaxy cluster, the background light was distorted and magnified. By carefully measuring these specific distortions, scientists could calculate the total mass of the foreground cluster. Time and again, the results were simply undeniable. The visible matter was only a small fraction of what was required. The vast majority of the mass was some form of invisible dark matter. While we cannot see it, this dark matter appears to follow relatively simple rules. It behaves quite differently from the ordinary matter that forms stars, planets, and indeed ourselves. Normal matter collides, heats up, and radiates energy away. But dark matter seems to interact almost exclusively through the force of gravity. It drifts through the cosmos without friction, never losing energy the way a cloud of gas does. This fundamental difference had enormous consequences for how the entire universe evolved. In the aftermath of the Big Bang, the cosmos was a nearly uniform sea of matter and energy, with only minuscule variations in density. Dark matter, unburdened by interactions with radiation, was the first to respond to gravity's persistent call. It began to coalesce around these tiny density fluctuations, while ordinary matter remained too hot and energetic to collapse. This crucial head start was everything. Over eons, these initial seeds grew into vast, invisible halos of dark matter, structures hundreds of thousands of light years across, that formed long before the very first stars ignited. As the universe continued to expand and cool, ordinary matter was gradually drawn into these pre-existing gravitational wells, carved out by dark matter. Within these invisible cosmic cradles, gas collected, compressed, and eventually grew hot and dense enough to spark nuclear fusion. This was the birth of the first stars. These stars then congregated into the first galaxies, but their locations were not determined by chance. They formed precisely within the deepest gravitational wells that dark matter had already prepared. In this sense, the visible universe was constructed upon a hidden blueprint, with dark matter sculpting the cosmic landscape and ordinary matter illuminating it for us to see. This intricate process gave rise to one of the most stunning patterns in all of nature, the cosmic web. When viewed on the grandest of scales, galaxies are not scattered randomly across the void. Instead, they are arranged along immense filaments of matter that stretch for tens and even hundreds of millions of light years. These cosmic threads intersect at dense nodes, where massive galaxy clusters are born. In between these filaments lie vast, empty regions known as cosmic voids. The overall structure is a breathtaking, three-dimensional network woven throughout the entire observable universe. For many years, this vision of a cosmic web existed primarily within the realm of theory and powerful supercomputer simulations. Cosmologists modeled the behavior of dark matter over billions of years, and these simulations consistently produced filamentary structures that bore a striking resemblance to the large-scale arrangement of galaxies that astronomers were beginning to observe. Now, the James Webb Space Telescope is helping to transform these predictions into concrete observations with unparalleled detail and clarity. By detecting hundreds of thousands of galaxies and precisely measuring their distances, the Webb telescope allows astronomers to create vast, three-dimensional maps of the cosmos. These maps reveal, in stunning clarity, galaxies tracing the long strands of the cosmic web, gathering in clusters at intersections, and leaving behind enormous voids where few galaxies reside. It is a powerful confirmation that the cosmic web is not merely a theoretical concept, but an observed and documented reality. Even more remarkably, these cosmic filaments act as channels for matter to flow. Gas and smaller galaxies are guided along these pathways by gravity, slowly migrating toward and feeding the larger galaxies and clusters at the nodes. This reveals that galaxies are not isolated islands drifting aimlessly through the void. They are deeply connected components of a single, vast gravitational network. Our own Milky Way galaxy is part of this grand design, embedded within a larger filament of this cosmic web. Over immense timescales, gravity continues to direct the flow of galaxies along these paths, constantly reshaping the large-scale structure of the universe. And yet, for all we have learned about its influence, the true identity of dark matter remains one of science's most profound and persistent mysteries. Scientists have put forth numerous theories. Some suggest it is composed of undiscovered particles that interact only weakly with ordinary matter. Other, more exotic ideas explore the possibility that it points to entirely new physics beyond our current understanding. All around the world, sophisticated experiments are searching for these elusive particles, while telescopes continue to map their gravitational effect. To date, however, no dark matter particle has ever been directly detected. Despite this lingering uncertainty, its presence is almost impossible to dispute. If we remove dark matter from our cosmological models, the universe we observe simply ceases to make sense. Galaxies would fly apart, clusters would fail to form, and the magnificent web of matter stretching across the cosmos would never have come into being. Dark matter provides the essential scaffolding upon which the visible universe is built. This cosmic construction takes place amid a constant tension. While dark matter's gravity works to pull structures together, another mysterious force, dark energy, is simultaneously stretching the fabric of space itself, pushing the most distant galaxies ever farther apart. The universe, it seems, exists in a delicate balance between these two invisible influences, one that builds structure and one that drives expansion. Together, they orchestrate the cosmic dance we see playing out across the heavens. The stars, galaxies, and glowing nebulae, captured by telescopes like Webb, are merely the luminous surface of a much deeper reality. Beneath this shining veneer lies a hidden architecture, an unseen framework that has guided the formation of everything we can see for billions of years. The James Webb Space Telescope has not shown us the edge of the universe. It has revealed something far more humbling. The deeper we gaze into the cosmos, the more we understand that what is visible may only be a faint echo of a much larger, unseen whole. We invite you to continue this journey of discovery with us here on Calm Space. Your support is what allows Calm Space to continue to grow.